lot of the integrals that we're asked to compute, they look close to one of your basic integration rules, but for whatever reason, they just don't fit quite right. And so one of the skills that we need to have or be really good at is rewriting integrands to mold or shape them to where they do fit one of your basic integration rules. And it's a skill. It takes a lot of practice, takes lots of trial and error and working lots of examples to get pretty proficient at this. But that's what we're doing in these videos. We're working through some of the common tricks, some of the common types of problems that you'll run into. And this is one in particular. So let's take a look at this one here. We have the integral of 1 over the square root of 2x minus x squared. Now, a student might, start off looking at this one, possibly thinking perhaps like u substitution, especially because you have the composition there with the square root and the terms inside the square root. But I think it's pretty obvious that that's not going to work, because if the u is 2x minus x squared, there's certainly no du on the outside. So I think that's out. You might briefly think possibly log rule because it's a fraction. I think we quickly ruled that out as well. That's clearly not going to work as well. About the closest thing to me that it kind of resembles is it kind of sort of feels like that arcsine integral. You have the integral of 1 over a radical. That's what made me think of this. But the problem is that this is not a squared minus u squared exactly, and so we have a bit of a problem because 2x isn't a constant like a is. Now, I'm not going to give up on this one though, because this one I think I can make this happen if I know the correct algebra steps to do. And so here's a very common algebra technique that we need quite a lot, in fact, and it's called completing the square. It's something we typically study in like a college algebra class a few years ago. We kind of glazed through it, but suddenly we need it again. And so it would be worth our time to review completing the square, because it's actually quite important. And if you didn't know how to complete the square, you really couldn't do this integral. And so it's important to brush up on these old algebra techniques like completing the square. So let's just recap. This is just a quick reminder. If you're completing the square, what you're trying to do is take like a quadratic, for example, and write it as a perfect square. That's why they call it completing the square. So we would prefer something like blank squared plus, such and such, plus something else. And the reason this already doesn't factor as a perfect square is really because of the c. If you had something like x squared, I'll just make this up, plus 6x plus 9, that would be a perfect square. It would be x plus 3 quantity squared. But if this was a 19, suddenly it's not a perfect square anymore. So if this guy fails to be a perfect square, it's his fault. It's the 19's fault. And so here's what we do. Here's what we do in regards to that. If you want a perfect square, we will push the c off to the side, kind of back it up a little bit back here, and then we're going to put a number that fits better. It might not be c, but it'll be some other number. And here's what that magic number is. It actually has to do with whatever b is. You take half of b, whatever b is, and then you square that number. Now, if you add that amount to keep everything balanced, we need to turn right back around and subtract that amount. So you always take half of b and then square it. One other thing I'll mention before I go to the next card is to complete the square, it's imperative that this guy has a coefficient of 1. If it's 2x squared or negative x squared or 5x squared, you can't complete the square until the leading coefficient is 1. But once it is, then you can complete the square by adding this number and subtracting it back away. All right, so let's try that for our example. If you notice the term under the radical that we were trying to complete the square on to make it fit this arcsine template was 2x minus x squared. So a little algebra first. Let's reorder these, put them in the right order. Negative x squared plus 2x. But this isn't quite right yet to complete the square. This has a coefficient of negative 1, not positive 1. So a common technique that I have to do quite often is I'll factor out this coefficient. Then on the inside, I'll have x squared minus 2x. X squared minus 2x. And this guy does have a coefficient of 1. So that's a good thing. All right, now what's that magic number I was referring to? What do? You take half of b, which is negative 1, and then you square that and you get positive 1. But as we said on the last card, whatever you add, you need to immediately subtract so that you don't mess up anything. So if we added 1, then we need to kind of in a way subtract 1. But all right, so this might throw you for a loop here for a minute. I know I wrote the symbol plus 1, but do you realize I actually subtracted 1 to the whole expression because of this negative out here? Because if you put the negative back through, you'd have negative x squared plus 2x minus 1. So we actually contributed minus 1 and we didn't realize it. So now, how do we account for that negative 1 that we added? Well, we are going to add 1. I know that feels counterintuitive because you just wrote plus 1. Why the heck are we writing plus 1 again? Well, it's because this isn't really plus 1. It's really minus 1. So you have to account for that coefficient if you have 1 on the outside. All right, there was no extra term here, so we don't really have anything else to do. And so let's clean this guy up a little bit. If I did it right, that trinomial in the parentheses should be a perfect square. Let's see if it is. X squared minus 2x plus 1 factors as x minus 1, I think you'll agree. So that would be x minus 1 quantity squared. It's a perfect square. That's great. Plus 1. And rewriting this guy, we would get 1 minus x minus 1 quantity squared. And that's perfect. That's perfect because that is a squared minus u squared. It's exactly the template that it needs to be in my integrand. Okay, so what is it? 1 minus quantity x minus 1 squared. So let me come back to this guy right here. So let me rewrite this. We have integral 1 over the big square root of 1 minus the quantity x minus 1 quantity squared, I believe it was, dx. These two guys are the exact same. They're just written in a different way. This guy completed the square on, where this guy I had not. This guy is a perfect fit to the arcsine integral. And so final answer, I know what a is, I know what u is. My final answer would be arcsine of u over a. Here's u, here's a. U over a, so x minus 1 over 1 plus c. And so we got our answer. So again, moral of the story, as with so many of these integrals, is you're given an integral. It doesn't quite fit anybody, any basic rule. So you work on it a little bit, you change things, you complete the square, you break it apart, you FOIL something, you do something to it to change it so that it fits one of your basic integration techniques.